Hello everyone, welcome to my channel. My name's Jasmine. And so this here, oh by the way, if you're watching this to get answers to the course material, I will not be doing that. So may as well go on their actual website, the TryHackMe website, and watch their videos that they offer, because I'm only making this video to practice my public speaking and pronunciation. So I will not be giving out answers or going through the labs. There's plenty of walkthrough videos on YouTube. So if that's what's happening, you have a good day, and thank you for stopping by. So, okay, this is, I'm going to be doing network fundamentals for the pre-security on TryHackMe. I'm just going to be reading it out loud. So, network fundamentals. Learn the core concepts of computers communicate with how computers communicate with each other and types of network weaknesses. What is networking? I know this is not going to be a really fun video. I'm just, like I said, I'm reading out loud. See, they have their own videos. It's probably a lot better than this one. So you go ahead and watch that. Okay, what is networking? Networks are simply things connected. For example, your friendship circle. You are all connected because of similar interests, hobbies, skills, and sorts. Networks can be found in all walks of life, which are a city's public transportation system, or infrastructure such as the national power grid for electricity. 3. Meeting and greeting your neighbors. Or 4. Postal systems for sending letters and parcels. But more specifically, in computer, networking is the same idea, just dispersed to technological devices. Take your phone as an example. The reason that you have it is to access things. We'll cover how these devices communicate with each other and the rules that follow. In computing, a network can be formed by anywhere from 2 devices to billions. These devices include everything from your laptop and phone to security cameras, traffic lights, and even farming. Networks are integrated into our everyday life, but be it gathering for the weather, delivering electricity to homes, or even determining who has the right of way at a road. Because networks are so embedded in the modern day, networking is an essential concept to grasp in cybersecurity. Take the diagram below as an example. Alice, Bob, and Jim have formed their network. We'll come onto this a bit later on. Also, if you're taking the CompTIA certifications like Network Plus or Security Plus, this course, this learning path, uh, goes into detail over OSI models, and that would be helpful as study material for your exam. Networks come in all shapes and sizes, which is something that we will also come on to discuss throughout this module. And I said I'm not going to be going through the answers. Either go on their website or watch their videos. Thank you. And what is the internet? Now that we've learned what a network is and how one is defined in computing, just devices connected, let's explore the internet. The internet is one giant network that consists of many, many small networks within itself. Using our example from the previous task, let's now imagine that Alice made some new friends named Zion and Toby that she wants to introduce to Bob and Jim. The problem is that Alex is the only person who speaks the same language as Zane and Toby. So Alice will have to be the messenger. Because Alice can speak both languages, they communicate to one another through Alice, forming a network. The first iteration of the internet was with ARPANET project in the late 1960s. This project was funded by the United States Defense Department and was the first documented network in action. However, it wasn't until 1989 when the internet as we know it was invented by Tim Berners-Lee by the creation of the World Wide Web, WWW. It wasn't until this point that the internet started to be used as a repository for storing and sharing information just like it is today. Let's relate Alice's network of friends to computing devices. The internet looks looks like a much larger version of this sort of diagram. Here. As previously stated, the internet is made up of many small networks all joined together. These small networks are called private networks, where networks connecting these small networks are called public networks, or the internet. So to recap, a network can be one of two types, a private network or a public network. Devices will use a set of labels to identify themselves on a network, which we will come on to in the task below. And it goes through the questions. Sometimes the questions are right there as I'm reading it, but that's only if you're actually listening. Task 3, identifying devices on a network. To communicate and maintain order, devices must be both identifying and identifiable on a network. What use is it if you don't know whom you're talking to at the end of the day? Devices on a network are very similar to humans. In fact, that we have two ways of being identified, our name or our fingerprints. Now we can change our name through deed poll, but we can't, however, change our fingerprints. Every human has an individual set of fingerprints, which means that even if they change their name, there is still an identity behind it. Devices have the same thing, two means of identification, with one being permeable. These are an IP address and a media access control, or MAC address. Think of this as being similar to a serial number. IP addresses. Briefly, an IP address or Internet Protocol address can be used as a way of identifying a host on a network for a period of time, where that IP address can then be associated with another device without the IP address changing. First, let's split up precisely what an IP address is in the diagram below. So that's octet 1, octet 2, octet 3, and octet 4. An IP address is a set of numbers that are divided into 4 octets. The value of each octet will summarize to be the IP address of the device on the network. This number is calculated through a technique known as IP addressing and subnetting. But that is for another day. What's important to understand here is that the IP addresses can change from device to device, but cannot be active simultaneously more than once within the same network. IP addresses follow a set of standards known as protocols. These protocols are the backbone of networking and force many devices to communicate in the same language, which is something that we'll come onto another time. However, we should recall that devices can be on both a private and public network, depending on where they will determine what type of IP address they have, a public or private IP address. A public address is used to identify the device on the internet, whereas a private address is used to identify a device amongst other devices. Take the table and screenshot below as an example. Here we have two devices on a private network. These two devices will be able to use their private IP addresses to communicate with each other. However, any data sent to the internet from either of these devices will be identified by the same public IP address. Public IP addresses are given by your Internet Service Provider, or ISP, at a monthly fee, which is your bill. As more and more devices become connected, it is becoming increasingly harder to get a public address that isn't already in use. For example, Cisco, an industry giant in the world of networking, estimated that there will be approximately 50 billion devices connected on the internet by the end of 2021. Enter IP address versions. So far, we have only discussed one version of the Internet Protocol addressing scheme known as IPv4, which uses a numbering system of 2 up to 32 IP addresses, which is 4.29 billion. So you can see why there is such a shortage. IPv6 is a new iteration of the Internet Protocol addressing scheme. To help tackle this issue, although it is seemingly more daunting, it boasts a few benefits. It supports up to the power of 128 of IP addresses, which is 340 trillion plus, resolving the issues faced with IPv4. More efficient due to new methodologies. The screenshot below compares both an IPv6 and an IPv4 address. So it's a lot longer. MAC addresses. Devices on a network will all have a physical network interface, which is a microchip board found on the device's motherboard. This network interface is assigned a unique address at the factory it was built, called a MAC, Media Access Control Address. The MAC address is a 12-character hexadecimal number, a base 16 numbering system used in computing to represent numbers. Split into twos and separated by a colon, these colons are considered separators. For example, I'm not going to read that out loud. The first 6 characters represent the company that made the network interface, and the last 6 is a unique number. So, vendor who build the network interface, in this instance, is Intel, so it's the first 3. And the unique address of the network interface is the last 3. However, an interesting thing about MAC addresses is that they can be faked or spoofed in a process known as spoofing. This spoofing occurs when a network device pretends to identify as another using its MAC address. When this occurs, it can often break poorly implemented security designs that assume that devices talking on a network are trustworthy. Take the following scenario. A firewall is configured to allow any communication going to and from the MAC address of the administrator. If a device were to pretend or spoof this MAC address, the firewall would think that it is receiving communication from the administrator when it isn't. Places such as cafes, coffee shops, and hotels alike often use MAC address control when using their guest or public Wi-Fi. This configuration could offer better services, i.e. a faster connection for a price if you're willing to pay the fee per device. The interactive lab attached to this task has been made to replicate this scenario. So it does a lab here. And the lab is to simulate a hotel Wi-Fi network where you have to pay for the service. You'll note that the router is not allowing Bob's packets, which are blue, to the TryHackMe website and is placing them in a bin. But Alice's packets, which are green, are going through fine because she has paid for Wi-Fi. Try changing Bob's MAC address to the same as Alice's to see what happens. That's the lab, but I will not be going through that. Please go on their website. Ping, which is ICMP. Ping is one of the most fundamental network tools available to us. Ping uses ICMP, which stands for Internet Control Message Protocol, packets to determine the performance of a connection between devices. For example, if the connection exists or is reliable. The time taken for ICMP packets traveling between devices is measured by ping, such as in the screenshot below. This measuring is done using ICMP's echo packet and then ICMP's echo reply from the target device. Pings can be performed against devices on a network, such as your home network or resources like websites. This tool can be easily used and comes installed in operating systems, or OSs, such as Linux and Windows. The syntax to do a simple ping is ping IP address or website URL. Let's see this in action in the screenshot below. So that's ping. There. Nope. Sorry. Here we are pinging a device that has a private address of 192.168.1.254. Ping informs us that we have sent 6 ICMP packets, all of which were received with an average time of 4.16 milliseconds. Now you are going to do the same thing to ping the address of 8.8.8.8 on the deployable website in this task. Pinging the correct address will reveal a flag to answer the following question below. In Task 5, continue your learning Intro to LAN. Oh, so it just goes to Intro to LAN room. Okay, so introducing LAN topologies, which is local area network for LAN. Over the years, there has been experimentation and implementation of various network designs. In reference to networking, when we refer to the term topology, we are actually referring to the design or look of the network at hand. Let's discuss the advantages and disadvantages of these topologies below. Star topology. The main premise of a star topology is the devices are individually connected via a central networking device, such as a switch or hub. This topology is the most commonly found today because of its reliability and scalability, despite the cost. Any information sent to a device in this topology is sent via the central device to which it connects. Let's explore some of these advantages and disadvantages of this topology below. Because more cabling and the purchase of dedicated networking equipment is required for this topology, it is more expensive than any other topologies. However, despite the added costs, this does provide some significant advantages. For example, this topology is much more scalable in nature, which means that it is very easy to add more devices as the demand for the network increases. Unfortunately, the more the network scales, the more maintenance is required to keep the network functional. This increased dependence on maintenance can also make troubleshooting faults much harder. Furthermore, the topology is still prone to failure or reduced. For example, if the centralized hardware that connects devices fails, these devices will no longer be able to send or receive data. Thankfully, these centralized hardware devices are often robust. Bus topology. This type of connection relies on a single connection, which is known as a backbone cable. This type of topology is similar to the leaf of a tree in the sense that devices or leaves stem from where the branches are in this cable. Because all data destined for each device travels along the same cable, it is very quickly prone to becoming slow and bottlenecked if devices within the topology are simultaneously requesting data. This bottleneck also results in very difficult troubleshooting because it quickly becomes difficult to identify which device is experiencing issues with data all traveling along the same route. However, with this said, bus topologies are one of the easier and most cost-efficient topologies to set up because of their expenses, such as cabling or dedicated networking equipment used to connect these devices. Lastly, another disadvantage of the bus topology is that there is a little redundancy in place in case of failures. This disadvantage is because there is a single point of failure along the backbone cable. If this cable were to break, devices can no longer receive or transmit data along the bus. Bus topology right here. Ring topology. The ring topology, also known as token topology, boasts some similarities. Devices such as computers are connected directly to each other to form a loop. meaning that there is little cabling required and less dependence on dedicated hardware, such as within a star topology. A ring topology works by sending data across the loop until it reaches the destined device, using other devices along the loop to forward data. Interestingly, a device will only receive data from another device in this topology, if it does not have any to send itself. If the device happens to have data to send, it will send its own data first before sending data from another device. Because there is only one direction for data to travel across this topology, it is fairly easy to troubleshoot any faults that arise. However, this is a double-edged sword because it isn't an efficient way of data traveling across a network, as it may have to visit multiple devices first before reaching the intended device. Lastly, ring topologies are less prone to bottlenecks, such as within a bus topology, as large amounts of traffic are not traveling across the network at any one time. The design of this topology does, however, mean that a fault, such as a cut cable or a broken device, will result in the entire networking breaking. What is a switch? Switches are dedicated devices within a network that are designed to aggregate multiple other devices such as computers, printers, or any other networking capable device using the Ethernet. These various devices plug into a switches port. Switches are usually found in larger networks such as businesses, schools, or similar sized networks, where there are many devices to connect to the network. Switches can connect a large number of devices by having ports of 4, 8, 16, 24, 32, and 64 for devices to plug into. Switches are much more efficient than their lesser counterpart, which are hubs and repeaters. Switchers keep track of what device is connected to which port. This way, when they receive a packet, instead of repeating that packet to every port like a hub would do, it just sends it to the intended target, thus reducing network traffic. Both switches and routers can be connected to one another. The ability to do this increases the redundancy or the reliability of a network by adding multiple paths for data to take. If one path goes down, another can be used. Whilst this may reduce the overall performance of a network because packets have to take longer to travel, there is no downtime, a small price to pay considering the alternative. What is a router? It's a router's job to connect networks and pass data between them. It does this by using routing, hence the name router. Routing is the label given to the process of data traveling across networks. Routing involves creating a path between networks so that this data can be successfully delivered. Routing is useful when devices are connected by many paths, such as in the example diagram below. And then it goes to the questions here. A primer on subnetting, which is task 2. As we previously discussed throughout the module so far, networks can be found in all shapes and sizes, ranging from small to large. Subnetting is a term given to splitting up a network into smaller, miniature networks within itself. Think of it as slicing up a cake for your friends. There's only a certain amount of cake to go around, but everyone wants a piece. Subnetting is you deciding who gets what slice and reserving such a slice of this metaphorical cake. Take a business, for example. You will have different departments such as accounting, finance, and human resources. And that's their example. Whilst you know where to send information in real life to the correct department, networks need to know as well. Network administrators use subnetting to categorize and assign specific roles or parts of a network to reflect this. Subnetting is achieved by splitting up the number of hosts that can fit within the network, represented by a number called a subnet mask. Let's refer back to our diagram from the first room in the module. As we can recall, an IP address is made up of 4 sections called octets. The same goes for a subnet mask, which is also represented as a number of 4 bytes, which is 32 bits, ranging from 0 to 255. Subnets use IP addresses in 3 different ways. 1 is to identify the network address, 2 is to identify the host address, and 3 is to identify the default gateway. Let's split these up to understand their purposes in the table below. Network address. Its purpose is that this address identifies the start of an actual network and is used to identify a network's existence. Explanation is, for example, a device with the IP address of 192.196.1.100 will be on the network identified by 192.168.1.0. The host address, its purpose is an IP address here is used to identify a device on the subnet. For example, a device will have the network address of 192.168.1.1, and a default gateway, its purpose is a special address assigned to a device on the network that is capable of sending information to another network. And its explanation is any data that needs to go to a device that isn't on the same network, i.e. isn't on 192.168.1.0, will be sent to this device. These devices can use any host address, but usually use either the first or last host address in a network, which is 0.1 or 0.254. Now, in small networks such as at home, you will be on one subnet as there is an unlikely chance that you need more than 254 devices connected at one time. However, places such as businesses and offices will have much more of these devices: PCs, printers, cameras, and sensors, where subnetting takes place. Subnetting provides a range of benefits including efficiency, security, and full control. We'll come on to explore exactly how subnetting provides these benefits at a later date. However, for now, all we need to understand is the security elements to it. Let's take the typical cafe on the street. This cafe will have 2 networks. One is for employees, cash registers, and other devices for the facility. 2 is one for the general public to use as a hotspot. Subnetting allows you to separate these 2 use cases from each other whilst having the benefits of a connection to larger networks such as the internet. The ARP protocol, which is task 3. Recalling from our previous task that devices can have 2 identifiers, a MAC address and an IP address. The Address Resolution Protocol, or ARP for short, is a technology that is responsible for allowing devices to identify themselves on a network. Simply, the ARP protocol allows a device to associate its MAC address with an IP address on the network. Each device on a network will keep a log of the MAC addresses associated with other devices. When devices wish to communicate with another, they will send a broadcast to the entire network searching for the specific device. Devices can use the ARP protocol to find the MAC address, and therefore the physical identifier of a device for communication. How does ARP work? Each device within a network has a ledger to store information on, which is called a cache. In the context of the ARP protocol, this cache stores the identifiers of other devices on the network. In order to map these 2 identifiers together, IP address and MAC address, the ARP protocol sends 2 types of messages, which is 1 ARP request and 2 ARP reply. When an ARP request is sent, a message is broadcasted on the network to other devices asking, what is the MAC address that owns this IP address? When the other devices receive that message, they will only respond if they own that IP address and will send an ARP reply with its MAC address. The requesting device can now remember this mapping and store it in its ARP cache for future use. This process is illustrated in the diagram below. In the DHCP protocol, Task 4. IP addresses can be assigned either manually by entering them physically into a device or automatically and most commonly by using a DHCP, which stands for Dynamic Host Configuration Protocol server. When a device connected to its network, if it has not already been manually assigned an IP address, it sends out a request, which is a DHCP discover, to see if any DHCP servers are on the network. The DHCP server then replies back with an IP address the device could use, which is a DHCP offer. The device then sends a reply confirming it wants the offered IP address, which is a DHCP request. And then lastly, the DHCP server sends a reply acknowledging this has been completed, and the device can start using the IP address, which is DHCP ACK. So an example of how it's done. And then it goes through the questions. Task 5, continue your learning with the OSI model. So it goes through a simulation. It's like a little game where you choose, or let's see here, actually, because I finished this learning path like 2 weeks ago. OSI model. Learn about the fundamental networking framework that determines the various stages in which data is handled across the network. Here's our video. It's a much better video than this, of course, but... Okay. Task 1. What is the OSI model? The OSI model, which stands for Open Systems Interconnection Model, is an absolute fundamental model used in networking. This critical model provides a framework dictating how all networked devices will send, receive, and interpret data. One of the main benefits of the OSI model is that devices can have different functions and designs on a network while communicating with other devices. Data sent across a network that follows the uniformity of the OSI model can be understood by other devices. The OSI model consists of 7 layers, which are illustrated in the diagram below. Each layer has a different set of responsibilities and is ranged from layer 7 to layer 1. At every individual layer that data travels through, specific processes take place and pieces of information are added to this data, which is what we'll come to discuss in the upcoming task within this room. However, for now, we only need to understand that this process is called encapsulation and what the OSI model looks like in the diagram below. 7 is application, 6 is presentation, 5 is session, 4 is transport, 3 is network, 2 is data link, and 1 is physical. Task 2, Layer 7 application. So this application layer of the OSI model is the layer that you will be most familiar with. This familiarity is because the application layer is the layer in which protocols and rules are in place to determine how the user could interact with data sent or received. Everyday applications such as email clients, browsers, or file server browsing software such as FileZilla provide a friendly graphical user interface, or GUI, for users to interact with data sent or received. Other protocols include DNS, which is Domain Name System, which is how website addresses are translated into IP addresses. Okay, oh, no answers to questions. Task 3 is Layer 6, presentation. Layer 6 of the OSI model is the layer in which standardization starts to take place. Because software developers can develop any software such as an email client differently, the data still needs to be handled in the same way, no matter how the software works. This layer acts as a translator for data to and from the application layer, which is layer 7. The receiving computer will also understand data sent to a computer in one format destined for in another format. For example, when you send an email, the other user may have another email client to you, but the contents of the email will still need to display the same. Security features such as data encryption, like HTTPS, when visiting a secure site, occur at this layer. Okay. Task 4 is layer 5, session. Once data has been correctly translated or formatted from the presentation layer, which is layer 6, the session layer, which is layer 5, will begin to create a connection to the other computer that the data is destined for. When a connection is established, a session is created. Whilst this connection is active, so is the session. The session layer, which is layer 5, synchronizes the two computers to ensure that they are on the same page before data is sent and received. Once these checks are in place, the session layer will begin to divide up the data sent into smaller chunks of data and begin to send these chunks, which are packets, one at a time. This dividing up is beneficial because of the connection. If the connection is lost, only the chunks that weren't yet sent will have to be sent again, not the entire piece of the data, which is, think of it as loading a saved file in a video game. What is worthy of noting is that the sessions are unique, meaning that data cannot travel over different sessions, but in fact only across each session instead. Task 5 is Layer 4 transport. Layer 4 of the OSI model plays a vital part in transmitting data across the network and can be a little bit difficult to grasp. When data is sent between devices, it follows one of the two different protocols that are decided based upon several factors, which is TCP and UDP. Let's begin with TCP, the Transmission Control Protocol. Potentially hinted by the name, this protocol is designed with reliability and guarantee in mind. This protocol reserves a constant connection between the two devices for the amount of time it takes for the data to be sent and received. Not only this, but TCP incorporates error checking into its design. Error checking is how TCP can guarantee that data sent from the small chunks in the session layer, which is layer 5, has then been received and reassembled in the same order. Let's summarize the advantages and disadvantages of TCP in the table below. Advantages of TCP is that it guarantees the accuracy of data. It also is capable of synchronizing two devices to prevent each other from being flooded with data, and it performs a lot more processes for reliability. Disadvantages of TCP is that it requires a reliable connection between the two devices. If one small chunk of data is not received, then the entire chunk of data cannot be used. It has a slow connection, which can bottleneck another device, as the connection will be reserved on the receiving computer the whole time. And TCP is significantly slower than UDP because more work has to be done by the devices using this protocol. TCP is used for situations such as file sharing, internet browsing, or sending an email. This usage is because these services require the data to be accurate and complete, which is no good having half a file. In the diagram below, we can see how a picture of a cat is broken into small pieces of data, which are known as packets, from the web server, where the computer reconstructs the picture of the cat into the correct order. Starts from web server and its packets are 1, 2, 3, and final, and then it sends to the computer. Now let's move on to the User Datagram Protocol, or UDP for short. This protocol is not nearly as advanced as its brother, the TCP protocol. It doesn't boast the many features offered by the TCP, such as error checking and reliability. In fact, any data that gets sent via UDP is sent to the computer whether it's there or not. There is no synchronization between the two devices or guarantee, just hope for the best and fingers crossed. Whilst this sounds disadvantageous, it does have its merits, which we'll lay out in the table below. Advantages of UDP is that UDP is much faster than TCP. Also, UDP leaves the application layer, which is user software, to decide if there's any control over how quickly packets are sent. And UDP does not reserve a continuous connection on a device as TCP does. Disadvantages of UDP are UDP doesn't care if the data is received. It is quite flexible to software developers in this sense, and this means that unstable connections result in a terrible experience for the user. Using the same example as before, we can now see that only packets 1 and 3 have been received by the computer, meaning that half of the image is missing. UDP is useful in situations where there are small pieces of data being sent. For example, protocols used for discovering devices, which are ARP and DHCP, that we discussed in Room 2, which is Intro to LAN, or larger files such as video streaming, where it is okay for some part of the video to be pixelated. Pixels are just lost pieces of data. Layer 6, which is Layer 3, network. So the third layer of the OSI model, which is network layer, is where the magic of routing or reassembly of data takes place from these small chunks to the larger chunk. Firstly, routing simply determines the most optimal path in which these chunks of data should be sent. While some protocols at this layer determine exactly what is the optimal path that data should take to reach a device, we should only know about their existence at this stage of the networking module. Briefly, these protocols include OSPF, which stands for Open Shortest Path First, and RIP, which stands for Routing Information Protocol. The factors that decide what route is taken is decided by the following. 1. What path is the shortest, i.e. has the least amount of devices that the packet needs to travel across? 2. What path is the most reliable, i.e. have packets been lost on the path before? 3. Which path has the faster physical connection, i.e. is one path using a copper connection, which is slower, or a fiber, which is considerably faster? At this layer, everything is dealt with via IP addresses such as 192.168.1.100. Devices such as routers capable of delivering packets using IP addresses are known as Layer 3 devices because they are capable of working at the third layer of the OSI model. Layer 2 data link. The data link layer focuses on the physical addressing of the transmission. It receives a packet from the network layer, which is including the IP address from the remote computer, and adds in the physical MAC, which is media access control address, of the receiving endpoint. Inside every network-enabled computer is a network interface card, which stands for NIC, which comes with a unique MAC address to identify it. MAC addresses are set by the manufacturer and are literally burnt into the card. They cannot be changed, although they can be spoofed. When information is sent across a network, it's actually the physical address that is used to identify where exactly to send the information. Additionally, it's also the job of the data link layer to present the data in a format suitable for transmission. Cascade is Layer 1 physical. This layer is one of the easiest layers to grasp, but put simply, this layer references the physical components of the hardware used in networking and is the lowest layer that you will find. Devices use electrical signals to transfer data between each other in a binary numbering system, which is ones and zeros. For example, Ethernet cables connecting devices such as in the picture below. And so it goes through this OSI game that I mentioned earlier. We'll not be going through that. Please go on their website. So we're on the section of packets and frames. Understand how data is divided into smaller pieces and transmitted across the network to another device. And they have their own YouTube video on this, which is better. Task 1, what are packets and frames? Packets and frames are smaller pieces of data that, when forming together, make a larger piece of information or message. However, they are two different things in the OSI model. A frame is at layer 2, which is the data link layer, meaning there's no such information as IP addresses. Think of this as putting an envelope within an envelope and sending it away. The first envelope will be the packet that you mail, but once it is opened, the envelope within still exists and contains data. This is the frame. This process is called encapsulation, which will be discussed in Room 3, the OSI model. At this stage, it is safe to assume that when we are talking about anything IP addresses, we are talking about packets. When the encapsulating information is stripped away, we're talking about the frame itself. Packets are an efficient way of communicating data across network devices such as those explained in Task 1. Because this data is exchanged in small pieces, there is less chance of bottlenecking occurring across the network than large messages being sent at once. For example, when loading an image from a website, this image is not sent to your computer as a whole, but rather small pieces where it is reconstructed on your computer. Take the image below as an illustration of this process. The cat's picture is divided into 3 packets where it is reconstructed when it reaches the computer to form the final image. Packets have different structures that are dependent upon the type of packet that is being sent. As we'll come on to discuss, networking is full of standards and protocols that act as a set of rules for how the packet is handled on a device. With billions of devices connected on the internet, things can quickly break down if there is no standardization. Let's continue with our example of the Internet Protocol. A packet using this protocol will have a set of headers that contain additional pieces of information to the data that is being sent across a network. Some notable headers include time to live, which this field sets an expiry timer for the packet to not clog up your network if it never manages to reach a host or escape. A checksum header, this field provides integrity checking for protocols such as TCP or IP. If any data is changed, this value will be different from what was expected and therefore corrupt. Source address header, this IP address of the device that the packet is being sent from so the data knows where to return. And destination address header, the device's IP address the packet is being sent to so that data knows where to travel next. Task 2 is TCP/IP, which is a 3-way handshake. TCP, or Transmission Control Protocol for short, is another one of these rules used in networking. This protocol is very similar to the OSI model that we have previously discussed in Room 3 of this module so far. The TCP/IP protocol consists of 4 layers and is arguably just a summarized version of the OSI model. These layers are 1. Application, 2. Transport, 3. Internet, and 4. Network interface. Very similar to how the OSI model works, information is added to each layer of the TCP model as the piece of data or packet traverses it. As you may recall, this process is known as encapsulation, where the reverse of this process is decapsulation. One defining feature of TCP is that it is connection-based, which means that the TCP must establish a connection between both a client and a device acting as a server before data is sent. Because of this, TCP guarantees that any data sent will be received on the other end. This process is named as the 3-way handshake, which is something we'll come on to discuss shortly. A table comparing the advantages and disadvantages of TCP is located below. Advantages of TCP: guarantees the integrity of data. It is capable of synchronizing 2 devices to prevent each other from being flooded with data in the wrong order, and performs a lot more processes for reliability. Disadvantages of TCP are it requires a reliable connection between the two devices. If one small chunk of data is not received, then the entire chunk of data cannot be used and must be resent. A slow connection can bottleneck another device, as the connection will be reversed on the other device the whole time. TCP is significantly slower than UDP because more work, also known as computing, has to be done by the devices using this protocol. TCP packets contain various sections of the information known as headers that are added from the encapsulation. Let's explain some of the crucial headers in the table below. Header, which is source port. This value is a port opened by the sender to send the TCP packet from. This value is chosen randomly, which are out of the ports from 0 to 65535 that aren't already in use at the time. Destination port header. This value is the port number that an application or service is running on, the remote host, the one receiving data. For example, a web server running on port 80, unlike the source port, this value is not chosen at random. Source IP header. This is the IP address of the device that is sending the packet. And destination IP header is this is the IP address of the device that the packet is destined for. Sequence number header. This is when a connection occurs, the first piece of data transmitted is given a random number. We'll explain this more in depth further on. And acknowledgement number header. This is after a piece of data has been given a sequence number, the number for the next piece of data will be the sequence number plus 1. We'll also explain this in more depth further on. A checksum header. This value is what gives TCP integrity. A mathematical calculation is made where the output is remembered. When the receiving device performs the mathematical calculation, the data must be corrupt if the output is different from what was sent. The data header. This header is where the data, i.e. bytes of a file that is being transmitted, is stored. And a flag header. This header determines how the packet should be handled by either device during the handshake process. Specific flags will determine specific behaviors, which is what we'll come on to explain below. Next, we'll come on to discuss the three-way handshake, the term given for the process used to establish a connection between two devices. The three-way handshake communicates using a few special messages. The table below highlights the main ones. Step 1 is its message is SYN, and this is where a SYN message is the initial packet sent by a client during the handshake. This packet is used to initiate a connection and synchronize the two devices together. Step 2 is SYNAC. This packet is sent by the receiving device, which is a server, to acknowledge the synchronization attempt from the client. Step 3 is ACK. This is the acknowledgement packet can be used by either the client or server to acknowledge that a series of messages/packets have been successfully received. Step 4 is data, which is once a connection has been established, data, such as bytes of a file, is sent via the data message. Step 5 is FIN. This packet is used to cleanly and properly close the connection after it has been complete. And the last step is the # hashtag, and its message is RST, which is this packet abruptly ends all communication. This is the last resort and indicates there was some problem during the process. For example, if the service or application is not working correctly, or the system has faults such as low resources. The diagram below shows a normal three-way handshake process between Alice and Bob. In real life, this would be between two devices. So it starts off from Alice's SYN to Bob, SYNAC, ACK. Any sent data is given a random sequence and is reconstructed using this number sequence, and incrementing by 1. Both computers must agree on the same number sequence for data to be sent in the correct order. This order is agreed upon during 3 steps. SYN, which is a client, here's my initial sequence number ISN to synchronize with 0. SYNAC, which is step 2, is the server. Here's my initial sequence number ISN to synchronize with 5000, and IAC, which is acknowledge your initial number sequence. Step 3 is ACK from the client, which is saying I acknowledge your initial sequence number ISN of 5000. Here's some data that is in my ISN plus 1. TCP closing a connection. Let's quickly explain the process behind TCP closing a connection. First, TCP will close a connection once a device has determined that the other device has successfully received all of the data. Because TCP reserves system resources on a device, it is best practice to close TCP connections as soon as possible. To initiate the closure of TCP connection, the device will send a FIN packet to the other device. Of course, with TCP, the other device will also have to acknowledge this packet. Let's show this process using Alice and Bob as we have previously. FIN from Alice, Bob sends an ACK and a FIN to Alice, then Alice sends an ACK. In this illustration, we can see that Alice has sent Bob a FIN packet. Because Bob received this, he will let Alice know that he received it and that he also wants to close the connection, which is using FIN. Alice has heard Bob loud and clear and will let Bob know that she acknowledges this. Task 3 is a practical handshake. It's a simulation lab that I will not be showing. Task 4 is UDP IP. The user datagram protocol, which is UDP, is another protocol that is used to communicate data between devices. Unlike its brother TCP, UDP is stateless protocol that doesn't require a constant connection between the two devices for data to be sent. For example, the three-way handshake does not occur, nor is there any synchronization between the two devices. Recall some of the comparisons made about these two protocols in Room 3 OSI model. Namely, UDP is used in situations where applications can tolerate data being lost, such as a video streaming or a voice chat, or in scenarios where an unstable connection is not the end-all. A table comparing the advantages and disadvantages of UDP is located below. Advantages of UDP are UDP is much faster than TCP, and UDP leaves the application or user software to decide if there's any control over how quickly packets are sent, and UDP does not reserve a continuous connection on a device as TCP does. The disadvantages of UDP are UDP doesn't care if the data is received or not. It is quite flexible to software developers in the sense, and this means that unstable connections result in a terrible experience for the user. As mentioned, no process takes place in setting up a connection between two devices, meaning that there is no regard for whether or not data is received, and there are no safeguards such as those offered by TCP, such as data integrity. UDP packets are much simpler than TCP packets and have fewer headers. However, both protocols share some standard headers, which are what is annotated in the table below. Header time to live, TTL. This field sets an expiry timer for the packet so it doesn't clog up your network if it never manages to reach a host or escape. Source address header, the IP address of this device that the packet is being sent from so that the data knows where to return to. Destination address header is where this device's IP address the packet is being sent to so that the data knows where to travel next. Source port header, this value is the port that is opened by the sender to send the UDP packet from. This value is randomly chosen. out of the ports from 0 to 65535 that aren't already in use at the time. And destination port header, this value is a port number that an application or service is running on the remote host, the one receiving data. For example, a web server running on port 80. Unlike the source port, this value is not chosen at random. And the last one is data header. This header is where data, i.e. bytes of a file that is being transmitted, is stored. Next, we'll come to discuss how the process of a connection via UDP differs from that of something such as TCP. We should recall that UDP is stateless. No acknowledgement is sent during a connection. The diagram shows a normal UDP connection between Alice and Bob. In real life, this would be between two devices. And here is the example below. Task 5 is Ports 101 Practical. Oh, and it's another lab simulation that I will not be showing. Please go on their website and continue your learning, extending your network. Extending your network, learn about some of the technologies used to extend networks out onto the internet and the motivations for this. Task 1, Introduction to Port Forwarding. Port forwarding is an essential component in connecting applications and services to the internet. Without port forwarding, applications and services such as web servers are only available to devices within the same direct network. Take the network below as an example. Within this network, the server with an IP address of 192.168.1.10 runs on a web server on port 80. Only the two other computers on this network will be able to access it, this is known as an intranet. Here's our example. So if the administrator wanted the website to be accessible to the public, which is using the internet, they would have to implement port forwarding like in the diagram below. With this design, Network 2 will now be able to access the web server running on Network 1 using the IP address of Network 1. It is easy to confuse port forwarding with the behaviors of a firewall, which is a technology we'll come on to discuss in a later task. However, at this stage, just understand that port forwarding opens specific ports, recall how packets work, and in comparison, firewalls determine if traffic can travel across these ports, which even if these ports are opened by port forwarding. Port forwarding is configured at the router of a network. Task 2, Firewalls 101. A firewall is a device within a network responsible for determining what traffic is allowed to enter and exit. Think of a firewall as border security for a network. An administrator can configure a firewall to permit or deny traffic from entering or exiting a network based on numerous factors such as where the traffic is coming from, which has the firewall been told to accept/deny traffic from a specific network, or where is the traffic going to? Has a firewall been told to accept or deny traffic destined for a specific network? Or what port is the traffic for? Has a firewall been told to accept or deny traffic destined for port 80 only? And the last one, what protocol is the traffic using? Does this mean does the firewall been told to accept or deny traffic that is UDP, TCP, or both? Firewalls perform packet inspection to determine the answers to these questions. Firewalls come in all shapes and sizes, from dedicated pieces of hardware, which are often found in large networks like businesses, that can handle a magnitude of data to residential routers like at your home, or software such as Snort. Firewalls can be categorized in 2 to 5 categories. We'll cover the 2 primary categories of firewalls in the table below. A stateful firewall This is a type of firewall that uses the entire information from a connection. Rather than inspecting an individual packet, this firewall determines the behavior of a device based upon the entire connection. This firewall type consumes many resources in comparison to stateless firewalls, as the decision-making is dynamic. For example, a firewall could allow the first parts of the TCP handshake that would later fail. If a connection from a host is bad, it will block the entire device. And a stateless firewall, this firewall type uses a static set of rules to determine whether or not individual packets are acceptable or not. For example, a device sending a bad packet will not necessarily mean that the entire device is then blocked. Whilst these firewalls use much fewer resources than alternatives, they are much dumber. For example, these firewalls are only effective as the rules that are defined within them. If a rule is not exactly matched, it is effectively useless. However, these firewalls are great when receiving large amounts of traffic from a set of hosts, such as a distributed denial of service attack, which is DDoS. Task 3 is a practical, goes through a lab. Oh, I'm not supposed to show you that, but it's a lab as to how to operate a firewall. Task 4 is VPN basics. A virtual private network, or VPN for short, is a technology that allows devices on separate networks to communicate securely by creating a dedicated path between each other over the internet, known as a tunnel. Devices connected within this tunnel form their own private network. For example, only devices within the same network, such as within a business, can directly communicate. However, a VPN allows two offices to be connected. Let's take the diagram below where there are three networks. Network 1 is Office 1, Network 2 is Office 2, and Network 3 is two devices connected via a VPN. The devices connected on Network 3 are still part of Network 1 and Network 2, but also formed together to create a private network, which is Network 3, that only devices that are connected via this VPN can communicate over. Let's cover some of the other benefits offered by a VPN in the table below. The benefits of a VPN is it allows networks in different geographical locations to be connected. It offers privacy. It offers anonymity. And so, for example, a business with multiple offices will find VPNs beneficial as it means that resources like servers and infrastructure can be accessed from another office. VPN technology uses encryption to protect data. This means that it can only be understood between the devices it was being sent from and is destined for, meaning the data isn't vulnerable to sniffing. This encryption is useful in places like public Wi-Fi, where no encryption is provided by the network. You can use a VPN to protect your traffic from being viewed by other people. Journalists and activists depend upon VPNs to safely report on global issues in countries where freedom of speech is controlled. Usually, your traffic can be viewed by your ISP and other intermediaries and therefore tracked. The level of anonymity a VPN provides is only as much as how other devices on the network respect privacy. For example, a VPN that logs all of your data and history is essentially the same as not using a VPN in this regard. TryHackMe uses a VPN to connect you to our vulnerable machines without making them directly accessible on the internet. This means that you can securely interact with our machines. Service providers such as ISPs don't think you're attacking another machine on the internet, which could be against the terms of service, and the VPN provides security to TryHackMe as vulnerable machines are not accessible using the internet. VPN technology has improved over the years. Let's explore some existing VPN technologies below. The VPN technology, which is PPP, This technology is used by PPTP to allow for authentication and provide encryption of data. VPNs work by using a private key and public certificate, similar to SSH. A private key and certificate must match for you to connect. This technology is not capable of leaving a network by itself, which is non-routable. The VPN technology PPTP, which stands for the point-to-point tunneling protocol, is the technology that allows the data from PPP to travel and leave a network. PPTP is very easy to set up and is supported by most devices. It is, however, weakly encrypted in comparison to alternatives. VPN technology IPsec, which stands for Internet Protocol Security, encrypts data using the existing Internet Protocol or IP framework. IPsec is difficult to set up in comparison to alternatives. However, if successful, it boasts strong encryption and is also supported by many devices. Cas5 LAN networking devices. What is a router? It is a router's job to connect networks and pass data between them. It does this by using routing, hence the name router. Routing is the label given to the process of data traveling across networks. Routing involves creating a path between networks so that this data can be successfully delivered. Routers operate at layer 3 of the OSI model. They often feature an interactive interface such as a website or console that allows an administrator to configure various rules such as port forwarding or firewalling. Routing is useful when devices are connected by many paths, such as in the example below, where the most optimal path is taken. Routers are dedicated devices and do not perform the same functions as switches. We can see that computer A, in this diagram, computer A's network is connected to a network of computer B by two routers in the middle. The question is, what path will be taken? Different protocols will decide what path should be taken, but factors include 1. What path is the shortest? 2. What path is the most reliable? And 3. Which path has a faster medium? Is it copper or fiber? What is a switch? A switch is a dedicated networking device responsible for providing a means of connecting to multiple devices. Switches can facilitate many devices from 3 to 63 using Ethernet cables. Switches can operate at both Layer 2 and Layer 3 of the OSI model. However, these are exclusive in the sense that Layer 2 switches cannot operate at Layer 3. Take, for example, a Layer 2 switch in the diagram below. These switches will forward frames, which, remember, these are no longer packets as the IP protocol has been stripped, and it goes on to the connected devices using their MAC address. These switches are solely responsible for sending frames to the correct device. Now let's move on to Layer 3 switches. These switches are more sophisticated than Layer 2 as they can perform some of the responsibilities of a router. Namely, these switches will send frames to devices, as Layer 2 does, and route packets to other devices using the IP protocol. Let's take a look at the diagram below at Layer 3 switch in action. We can see that there are two IP addresses, 192.168.1.1, and the other IP address is 192.168.2.1. A technology called VLAN, which stands for Virtual Local Area Network, allows specific devices within a network to be virtually split up. This split means that they can all benefit from things such as an internet connection, but are treated separately. This network separation provides security because it means that the rules in place determine how specific devices communicate with each other. This segregation is illustrated in the diagram below. This is the sales department, VLAN 1, and then this is the accounting department, VLAN 2. And then it goes on to the questions. And then there's a practical network simulator. The simulator is to deploy the static site attached to this task, and then and experiment with the network simulator. The simulator will break down every step a packet needs to take to get from point A to point B. Try sending a TCP packet from computer 1 to computer 3 to reveal a flag. And I will not be going through that. And so that is the last of network fundamentals on the pre-security learning path. Thank you so much for watching, and you have a good day.